Now let's get my whiteboard up. And we should have a whiteboard on the screen, folks. Hi.
Yep, can see it.
Right, off we go. Right, let's recap on the essential things from the last lecture. And we were looking at window operators. And the two operations I went to in detail, first of all, was the low pass filter. And these are filters for images, not for signals, as you might get in electronics. And the low pass filter was a window 3 by 3. What were the coefficients in the window? Low pass filter. Silence. The coefficients are all ones. And you correlate that with an image. So you've got a large image. And that high pass filter window scans the image. Let's draw it 3 by 3. It's moving across and it's moving down on the real image. And it produces a pixel at the position of the center of the window. So if the window is looking at an image area, let's draw some pixels that have 4 bits resolution, so we can have values 0 to 15. If it's looking at 0, 1, 3, 4, 5, 7, 12, 14, and 15, those would be the pixel intensities under the window. The correlation of this window with that part of the image would give you 1 times 0 is 0 plus 1 times 1 is 1. In fact, you simply add up all the pixels in the window because the weighting is 1. 5 plus 7 plus 12 plus 14 plus 15. And I can add that up myself. 15, 14, 29, 39, 41, 48, 53, 57, 60, 61. I think that's correct. It doesn't matter if it's wrong. Now, that is out of range. If I'm using 4 bits, because this was 4-bit resolution, and 4 bits is 0 to 15. And the range we can have in correlating that low pass window with an image, the lowest value we can get from the filter is when it's looking at all zeros, i.e. an area of total blackness, and the range is going to be 0 to the maximum range is when the window is over a total white area. In this case, they would be values 15. In 8-bit images, it would be 255. 4 bits, 15. There's 9 of them. 15 nines. What's 15 by 9? 90, 135. Or in terms of image, it's 0 to 9 times W, where W would be 15. So the range is 0 to 9W. We need a range of 0 to 15 to display the filtered image on our imaging system. The imaging system resolution, the pixel resolution is fixed. It's 4 bits. Absolute white is 15. So the correction factor is divide the window, correlate it with the image. There's all your ones. And you divide by 9. Each pixel by 9. And that will bring the image into range. Now, low-pass filtering will remove abrupt changes in intensity, which are high-pass effects, useful if you're using an entable neural network for pattern recognition. So as a pre-processing technique, it has its uses. So that was the low-pass filter. The high-pass filter at least the simplest one, which I gave you last week, again a 3 by 3 window operator. Would anybody like to suggest to me what the coefficients are in the operator windows? Yes, yes. I've got full screen. Let me go back. They are -1, -1, -1, -1, -1, -1, -1, -1, plus 8. And that emphasizes the difference between the center pixel and its neighbors. And you correlate that with an image. And if you work out the theoretical range of outputs, is going to be the lowest case is when the image is totally white and the center pixel is black. So that would be an image to draw it looking like that. We would have a black one in the center, assuming black is 1. Or no, yes, that's right. Black is in the center, and the outside is white. So this would be W, this would be 0, and we would have -8W, and the 0 in the center times 8 would be 0. So -8W. -8W. 2. The highest response is the inverse of that image. And that would be where we have a white center and absolute black pixels around the outside. So it is going to be, in this case, we're multiplying 0 by -1. All the minuses disappear. The center is W, and it's times 8. It's going to be to plus 8W. Now, you might think to normalize that and bring that in the range 0 to W to display the image, you would shift the pixels by 8W to give a range of 0 to 16W and divide by 16. Now, I'm not going to write that down because that is what you should not do, because these image windows that give these limits to the range, i.e. a black speck on a white background and a white speck on a black background, they are insignificant in terms of the appearance of the image. You can't see them. They are hidden away. They are at the pixel level. And they are most probably arising because of faults on the CCD array. This could be a single CCD array stuck to 1. This could be stuck to 0 or the other way around, depending on the electronics. So they are not important image features. And if we normalized to these extremes, you would find all the useful information would be compressed into a very narrow band of intensities, and the effect wouldn't be satisfactory. So the normalization you would use with high-pass filter, the correction factor you would use with high-pass filter is normalization. That means having filtered the image, get the histogram. You would have -8W there, you would have +8W there. Ignore those extremes. We would have information on the histogram somewhere maybe like that, where 0 might be in the middle. This would be -G min. Oh, this would be G min, which would be negative. This would be G max. and you would apply the standard normalization, G min to 0 by a shift. And then having shifted G min to 0, we would have G max minus G min, having shifted it, has to go to W. And that would be a multiply. And that would give you a high-pass filtered image. Now, I can't remember where I finished exactly last week, but I will repeat this if indeed I covered it. There is a problem with high-pass filtering. And that is if the if the window is on a constant area of intensity, for example, if the image is, say, all 7s, intensity 7, grayish, then applying the filter, the output pixel will be 0, black. And all constant areas doesn't matter what their value, they can be all black in the original image or all white or any intensity value in between. If they're all the same, all the constant areas of image go to black after filtering. So effectively, we have lost the, sometimes people call it the DC part of the image. Whatever the background, it always goes to black, and the image shows up with the high intensities only. Or high intensity changes, I should say. So in the notes on Blackboard, there are some pictures of high pass filtering, and you will see that they look like an edged image, which is quite useful if you're looking for edges. But if you want to use the images for human consumption and you want to return the background, there is a compromise we can use. Add, using an image add, original image. And that will restore the background different colors or shades, and it will show the enhanced edging. So, and the add algorithm, of course, is the output Cij equals Aij plus Bij, the 2 pixels you're adding. This would be the filtered image, this would be the original if we're doing this correction factor, and the correction factor is divide by 2. So that's where we were last week. Right, there's one more image class of operators I want to look at, and this involves double windows on an image. But one topic I should have covered with the equalization, the normalization section a couple of weeks ago, was image equalization. And so I want to talk about that pretty well for the rest of this session. Now make sure you understand the difference between image equalization and normalization. Right. Normalizing images. You take the histogram of the image, you find G min, and you find G max. And there is a series of histograms in between. And you transform that histogram to intensity ranges 0 to W. So G min goes down to there, and G max, in fact, take the white over there so it looks slightly more realistic. Let's extend that. And G max goes to W. And that will improve the quality of the image. If you want to be selective and look for information and make information in the darker region or the brighter region of the image clearer, then you can do band normalization or selective normalization. And in selective normalization, we take the original histogram, G min and G max, and supposing the histogram is something like that. Remember, this is number and this is intensity. And supposing we wanted to find or enhance the middle part of the histogram, say G min, G 50%. So we want to enhance the image in this range. We can take the normalization algorithm and we can take G min to 0. We can take G 50% to W, and of course all the pixels above G min become white. They saturate and we lose that information, but we've enhanced the lower part of the histogram. So that is selective normalization. It can be done in the top end of the histogram. It can be done in any region whatsoever. But supposing you want best quality image. With no loss, no whiteout, and no blackout. And this is equalization. So let's take a histogram and number against intensity. And supposing we have let's draw it as a continuous curve. Supposing we've got a curve that looks something like that. That would be my G min, and this would be G max. In fact, I'll draw it as an analog function because it will then be clearer rather than putting in the individual. Supposing the curve is something like this. That is G min and G max. Now what I want to do is I want to enhance the lower half of the histogram and the upper half of the histogram so that the equalized histogram has equal populations of intensities across the whole intensity range. Now, some books And what they're saying there is take the original histogram, the equalized histogram will be like that, with a series of individual equally spaced populations across the intensity range. Now, if you're doing that, you are losing image information. And if the images were used, say, for forensic purposes, and you were involved in a case and there was photographic evidence, and the images had been equalized, you could claim that those weren't the original images and they had been tampered with. For example, if I have a histogram which is just two entries, a series there and a series there, entry there. So these would be two populations at G1 and G2. If I were to equalize those using a flat histogram, the result would be at G1 and G2. We have to increase the number of G1s and we decrease the number of G2s, and that is flat or equal. Now, the pixels at the higher intensity we have changed and made lower. How do you select them? It's an arbitrary process, and of course you're changing the nature image. So the equalized histogram using this flat distribution is a corruption, and if you like, a alteration, a corruption of the image. The better approach for equalization is band equalization. And in band equalization, let's take a distribution like that. G min, G max. And I'll take the simple example using two bands. If two bands, I'm going to have a range of 0 to W/2 where I want half the pixels to be, and W/2 to W the other half, equal distributions within bands. So I need to find the G 50%. That is the midpoint of the distribution. And let's call this band A and this band B. If I'd drawn it absolutely accurately, they should have equal number of pixels in them. So for band A, I'll go away. Right, and take band A out of the histogram. There's going to be G min, and there's going to be G 50%. And I'm going to have a distribution that looks something like this. And that is band A. 1, shift to 0. And 2, well, let's do the shift as one step. The K, of course, is going to be minus G min. And we are now going to get band A going from 0 to G 50% minus G min. Effectively, we're normalizing within the band. The second step is a multiply. And the multiply, the K factor is going to be W/2, because we want to take the brightest in the A band to the halfway intensity, W/2, divided by G 50% minus G min. So there is your multiplication constant. And having done that, we're going to get the lower half of the histogram like this. and that is going to be 0, and this point is going to be W over 2, and that is going to be normalized over W over 2, 0 to W over 2, and if my drawing is correct, it will look something like that. So that is band A, normalized across the lower half of the intensities. Right, that's all straightforward. That is standard normalization. Now, what about band B? Now, the problem with band B, if we start trying to normalize in the original histogram, the lowest values are non-zero, and any multiply and shift, well, certainly the multiply, will likely to move this band completely out of range, will get whiteout. So the first step to avoid this whiteout is to shift band B to 0. Well, let's draw band B to start off with. Band B is going to be extracting it from the original histogram. It's sitting at G 50%, and it goes to G max. And what was the shape? Oh, it's something like this. And there was our band B. So the first thing to do is shift to 0. And that is going to be a K equals minus 50%. And we're now going to get a histogram 0, and that is going to be the start of the B band, and it is going to go down to that value. It now becomes G max minus G 50%. Now, having got the upper band at the black region of the histogram, you can now do a multiply and the intensity multiply applied to this shifted histogram. This is B, of course. It's not going to move the black one. Multiplying 0 by anything keeps it 0. But this we can now take to the halfway point, W over 2. And so if I multiply by K, the multiplying constant is W over 2 divided by G max minus G 50%. It's going to take this point to W over 2. 0 will be anchored at 0, and it will spread it over half the intensity band. So we will now get band B. Zero to W over 2, and that shape is going to be transformed, spread out, and it's going to be something, whatever it is, like that. And there is my band B spread out, which is fine, but it's now in the wrong place. It's at the bottom end of the histogram. That is the top range of intensities. It's got to be spread over the brightest half of the histogram. So the next step is now shift band B to W over 2 to W range. And the constant shift, K, is plus W over 2. In other words, I'm adding W over 2 to everything here, and we will now get the shifted band going from 0 to W. It's now at W over 2, and that band is going to be there, and it's going to come down, whatever it is, band B to W. So we've now got band B in the right place, and it's covering the top half of the intensities. Right, so far we're nearly there. We now need to combine with the shifted or normalized band B. Band A, I mean. So we now combine the two. So going back in the notes, get the normalized band A, the normalized band B, which is that one there. It is going to be between 0 and W. Midpoint is W over 2. And the histogram will look something, whatever it was, with band A there and band B there. We haven't lost any information, but we've optimized the band A. It's now covering half the pixel, bottom darkest half pixels over the lower 50% of the intensity. The same for band B, 50% of the pixels, the brightest ones, are now ranged between W over 2 and W. So that would be the best way of getting maximum information from the dark region and maximum information from the white region. But that is a histogram. So we're not there yet. We're doing image processing. We need an image. So having got the equalized histogram, we now need to obtain the pixel update table. And the pixel update table means we go back to the very first histogram. Where was it? There we are. We find the first value in the histogram. Let's put a blue there. Supposing that was the first value there. This is G min. Where does G min go into the final histogram? Well, of course, it goes to 0. That was an obvious one. It now becomes there. Let's take one in the middle. Supposing that was, let's have GX there. Gray level intensity X. We've got to find out where that has gone in the updated. It might well be there. That was GX, and this was the updated new value of GX. The same way as we did in the normalization. So you will end up with a table of input pixel values and output. These were the values in the first histogram. These were the values of the pixel intensity in the equalized histogram, 0, 1, 2, 3, and whatever it is. And that's your pixel update table, and that will lead you to your equalized image. So that is equalization to improve the quality. Oh, you silly machine. Okay. Right. That's a 2-band case. You could extend this idea to more bands. If we were taking 4 bands, I'll just outline the process there. For 4 bands, the histogram, something like that, we would find the regions that contain 25% of the pixels. So this would be band A, this would be band B, band C, and band D, G min, G max. This would be G 25%, G 50%, G 75%, and G max. And it would be exactly the same overall strategy, except you would have more bands. Step 1, band A to 0 to W over 4, a quarter of the intensities, which could be done by taking band A, a shift and a multiply. Then for the other bands, band B, shift it to band A, or 0, normalize to W over 4, and then having got the band normalized, the second band normalized over a quarter of the intensities, you now shift it to W over 4 to W over 2. And the same will be true for the third band. Shift it to 0, normalize it over a quarter of the intensities, and then shift it back to G50 to G75. And the fourth band, there's no W over 2 to 3/4 of W over 2, 3/4 of W. Final band, shift to 0, expand over a quarter intensities, and shift it back to the top half. So now that's the general principle. I have yet to ask a question of a 4-band equalizer in an exam, but you might be asked to describe the strategy if you're lucky. Okay, it's coming up to 1:45. Now we've got 10 minutes left. I don't want to start on edge detection now, so we can switch to seminar mode for 10 minutes if anybody's got any questions or queries. I've been getting a few emails, so you have been working on this, which is pretty good. But any questions so far? Silence. Anybody there? Nope. Okay, interesting point. Interesting observation with image processing. The operation. Here is your filter operator window. And let's call these pixel values I1, I2, I3, I4, I5, I6, I7, I8, and I9. And let's have another window for the filter operator. And they have constant values. Let's call them W1, W2, W3, W4, W5, W6, W7, W8, and W9. And we are correlating those two. The operation we are performing, we are multiplying the window operator coefficient with the pixel value. We are calculating W times W1 times I1 plus W2 times I2 plus all the way through to W9 times I9. What we are calculating is sigma I equals 1 to D of Wi times I. Recognize that operation? That is the operation of a neural network. The analog. The McCulloch-Pitts model. Oh. I've lost my whiteboard. So, image processing can be regarded as a neural network operation, except in image processing, we know the weights. Which are the weights for the filter in the case of the low pass filter, or the high pass filter, more interesting. High pass, the weights are -1, -1, -1, -1, -1, -1, -1, -1, +8. So those are the weights. We know them at the start of the operation. In a neural network application, we don't know the weights. We have to learn them. And this idea that the two operations are very similar can lead to an interesting idea. Can we learn image processing functions? And that is quite an interesting area of research at the moment. Okay, I'll leave you with that thought. We're finishing 6 or 7 minutes earlier. I'll hang on if anybody has any questions. Otherwise, we'll meet up again next Friday. So have a good weekend, folks, and start doing a bit of revision, because time is passing. Exams are looming. We're thinking about your exam questions right now. Okay, bye for now.